Welcome to today's Nečas seminar on continuum mechanics. It's for me to welcome here Ondřej Marek from the Faculty of Nuclear Sciences and Physical Engineering. He is still a master student at the faculty, nevertheless he has already several interesting results, and he will talk on the lattice Boltzmann method for compressible fluid flow and drag coefficient. So please take the floor.
Thank you for the introduction, and I would like to thank the organizers for inviting me here. Today, as it was mentioned, I would like to first, thank you. As it was mentioned, I would like to present the theory of the Lattice Boltzmann method and special part of it, which can be applied more at the compressible fluid flow, which is more suitable for it. And then the application would be modeling fluid flow in a channel and calculating the drag coefficient of some obstacles for increasing the Reynolds numbers by increasing the inflow velocity, and performing in a comparison on multiple obstacles with the same setup. So firstly, I would like to give a brief overview of the fluid dynamics, which I think most of you know more than me. And then I would like to give you a deeper understanding of the Lattice Boltzmann method, how it can be, how it works, how can it be derived, and how can it be used. And then I will talk more about the boundary conditions, which for the model I was using for the compressible fluid flow. There are some complications to it, as we will see in the section 2. And then I would like to present the numerical results on multiple cases, some convergence studies, and the studies for the drag coefficient. So the fluid dynamics. Just to recap, what is important for us for the explanation of Lattice Boltzmann method, we have some quantity which is changed by the diffusion and by advection. From this come the two views that it either changes in the Eulerian sense that there is no advection, or we are looking at it in a from the stationary view, or there is the material derivative. Here, I would point out that the macroscopic velocity of the quantity is here in the material derivative, and that will be imported from the Lattice Boltzmann method. So the problem we are solving now, there's those equations here, because the model I was trying to use can be also extended for the thermal fluid flow, but I constrained myself only for the isothermal case. So only the Navier-Stokes equations in this form. And the problems, basically both of them are in channels, both setups which I've been using. The boundary conditions, here the plus boundary conditions. This is basically a wall on the bottom and on the top in 2D, and periodic condition for the convergence studies, or inflow and outflow for the drag and lift. And just explanation of the stress tensor, or the notation here, which will be useful for deriving the stress tensor, which consists of the pressure and the dynamic stress tensor. Then the dynamic stress tensor also has the trace of the T matrix, which will be also very important for comparing the drag and lift with compressible assumption and without the compressible assumption, because the trace, the compressible case is 0. And now we are moving to the Lattice Boltzmann method. We are starting here on the left in Continuum, in macroscopic Navier-Stokes equations, and we are trying to zoom in on the Continuum. And if we zoom in too much, we get into the microscopic scale, where we have the individual particles. For this, there are methods like the Monte Carlo method, which has the random number generator and some randomness to the collisions of the particles, or it can be reduced. Here is the smooth particle dynamics, which takes particles which are just imagine they are just a reduced version of the physical particles, and their collisions are also smoothened out, so that there is no like randomness to the collisions. So sometimes the SPH is in mesoscopic or in microscopic, but in between the microscopic and the macroscopic are the mesoscopic, where we represent not the particles, but also not just the continuum, something more. And there lies the Lattice Boltzmann method, which basically, to start, describes at one point in space and time, not only the macroscopic quantities, but also the particles itself. So here in 2D velocity space, denoted by C, we have some distribution of velocities of particles. Everything is just probabilistic, so no particles moving the particular microscopic velocity, but in some area, just like in continuum, but now the small area is now also in the velocity space, not only in spatial and time or spatial. And for this, because we are in statistics, we can try to look at the values which describe the distribution function, the probability distribution, and we can describe them by the statistical moments. So the zeroth moment, just a normalization factor. If we add up all the particles with different microscopic velocities at one place, we get just the density, because we now have all the particles which are at that point. And if we multiply by microscopic velocity in each direction separately, like this, form it into a vector, we actually get, again, the normalization factor, and then the macroscopic velocity, because the mean value, as you can see here, this was actually the maximum in the center. And this is equilibrium distribution, which I will get to in a moment. But the mean here is the maximum value, because this is just a Gauss distribution, which is symmetric in each direction. So the mean is the macroscopic velocity. And similarly, in the thermal case, which then I model only to conserve energy, but not to change the temperature. Here we add the second moment in each direction, add the 1/2 to have it like in the form of the kinetic energy, here it's specific. And here the 3/2, they are basically in 3D by assuming we have ideal gas, and there is the velocity squared and everything half to have the discrete kinetic energy. This is the discrete total energy. This is the kinetic part, and this is the internal part, internal energy. And the equilibrium distribution, which I showed before, is the Maxwell-Boltzmann distribution, which comes from statistical physics for ideal gas, which also shows to work even for fluids, general fluids. So here in 2D, the Gauss distribution, or physicists use it more just for the velocity norm in 1D, just to see which velocity the particles have. And here are some statistical moments for the equilibrium, which are to a higher order, because that's how the models are then derived. So basically, this was like one part of my study now for the diploma thesis. I basically just derived an exact formula for each of the statistical moments of this function, which is used in articles, but never actually written out in one form. So here even we can see here the mean, the velocity, the energy, and then there are some very interesting ones, but too complicated to understand. But they're also used for the velocity models, which I will show in a moment. And now that we have a method how to describe now our mesoscopic scale, the continuum. We need to know how it changes. So the change is basically the collision operator. It changes by interacting with each other and some outer force, and the change is given just by the total derivative. So it has three elements, deriving partially by each of the arguments. And here we can see that part I shown in the beginning in another slopes. Before it, here is the material derivative, just in the change that we have actually the microscopic velocity C, not only the macroscopic velocity, because now the F, the quantity, is specific to each of the particles moving in specific direction with their specific microscopic velocity. And the change of the C, the change of the particle's microscopic velocity, is given by the specific force. And this is altogether is equal to the collision operator, the change. And here the conservation of moments is basically given by integrating over the collision operator over the change, so that basically here, if we change the integral and derivative, we get that the density is zero from the first moment, and the velocity and the change of energy is zero, or the change of each of these variables is zero altogether. And the simplest one is that at each time the particles, as they are interacting with each other, are approaching equilibrium at some speed given by the relaxation time. It will be shown that it depends on the viscosity of the fluid. If you have high viscous fluid, it converges very swiftly to the equilibrium. And what also needs to know, is that because the particles, the universe is moving in one direction, the entropy is always increasing. Then if we write the entropy in the continuous case as the distribution times logarithm of the distribution over the whole microscopic velocity space, it needs to increase in this form. And it actually holds. That's how the equilibrium Lattice-Boltzmann is derived. That the equilibrium is the maximum at with some general moments, with some density, velocity, and energy, or the energy is given by the temperature. So now this is all in continuous case, but in discrete case, we need to now represent it in computer. So for the domain and the time, we just discretize it into time steps, delta t here, and the domain is now discretized into a uniform grid. That's the specification of the Lattice Boltzmann method, because when we discretize the distribution function f, we have the whole velocity space, which we need to somehow represent. So we represent it at some points here, even though it's not seen that clearly. There is also the velocity zero, the particles which are not moving. And then symmetrically to each direction, we have velocities which need to be, these diagonal need to be scaled more to the square root of 2 to end up at the next step in the uniform lattice. And the change is basically given by, this is the form that comes from the material derivative. Each distribution function changes. This is the argument, the value at the right hand side, and it changes, but it changes and it moves according to its microscopic velocity. So maybe it's a little bit further. Here I would like us to note that the Batagard-Gross-Krug operator that we are approaching equilibrium can also be discretized for each of the discrete velocities. I will get to what the discrete equilibrium is in a moment. But yeah, here just there is also a non-dimensionalization step needed. We can't just use the physical dimensions. because we need to move in the lattice where everything is scaled, basically scaled, so that the delta t is 1, that the time step is actually like just index, and the lattice is also just indexed by the delta x. Every step is 1, and we are coming from here. I denoted by a small delta, where we are keeping the Reynolds number of the simulation. Here, just reference velocity, reference length, like the length of the object, and reference viscosity. For me, it's just constant in the whole space, so it's just the viscosity of the fluid. And then we can choose if we are scaling by keeping the non-dimensional viscosity, or if we are keeping non-dimensional velocity. There are two options because the Reynolds number gives only one constraint. So that will be shown in the result and comparison of this. And the microscopic variables can be discretized. The integrals are discretized to just sums over the distribution functions. Here, the only change which comes from the analysis back to the convergence to the Navier-Stokes equations is just that for the velocity, there is also the forcing term, which is here we are like adding half a force, again specific force, and ideal gas. And just to show it more visually, we have some distribution functions here, 8 arrows, and one is the distribution function which beholds the particles with microscopic velocity 0 behold it. And in each time step, these particles somehow collide. The collision, as can be seen here, depend only on the values that are at that point. They are just computed locally, and then they are shifted in the lattice according to the macroscopic velocity. And everything can be collided at once. Here, every distribution function just depends on the ones with the same color at the same lattice side, and then they shift all together. So this is the collision, the change in the values, and this is the streaming part. And this can be done for the model I showed on the previous slide, but this model with more distribution functions, more microscopic velocities can supposedly represent or model fluid flow that's compressible more better. So that's why I was using it. And this one, basically, when it's streaming, the large microscopic velocities stream further into the lattice. And yeah, here just the two steps. So firstly, we recompute the microscopic distribution functions and add the collision and some forcing operator, and then we are shifting in the lattice, and everything these steps can be parallelized. And just to note the discrete equilibrium, basically, first method to approximate the Maxwell-Boltzmann distribution is to use the Hermite polynomial here to the second order. And the Hermite polynomial is used because it best then approximates the integrals because of Hermite quadrature formula. But one model I was also using for the equilibrium is the entropic model, which basically here extremizes the discrete entropy. Here it minimizes it because there is no minus sign, which is used often in the Lattice Boltzmann method literature. So it minimizes it with these constraints. I will skip over the details of the minimization, but basically it just is doing a Newton method for a Lagrange function of this problem with these Lagrange multipliers. Basically can be solved up to every distribution function can be solved and only the Lagrange multipliers are unknown. So basically in 2D, we are solving a four equation system by using the Newton method. So multiplying 4 times to 4 matrices and symbolically inverting them and trying to converge to the extremum. And yeah, it's modified Newton method. It also the step also decreases exponentially. And here to overview the Lattice Boltzmann method, we have the domain omega and time interval, which is discretized. So for each point in the discretization, we have this equation. And here I just added the collision operator, and now there is no forcing term, which is included only in the convergent studies. And from this term, if we are doing Chapman-Engstrup analysis for convergence to the numbers of equations, we get that this tau, this transition time now in the discrete form, has to be equal or has to satisfy this relation with the viscosity. And basically, if tau, just to give an intuition, if tau was 1, at each time step, because delta t is 1, we would just plug the equilibrium to each point according to the streaming. So it would just move a little bit, but that's called the equilibrium Lattice Boltzmann method. And here just the forcing I used is called Cooper-Shrug, but I won't make it harder to understand, because there is like 2 different velocities to add the forcing term, but we'll stick with this definition for the intuition behind the Lattice Boltzmann method. And for the boundary conditions, now here it's only on the lattice on the fluid nodes, but on the boundary conditions, there are additional nodes added, and on them, we apply rules to approximate the physical boundary conditions which are in the Navier slopes. So here are basically, I've done multiple ball boundary conditions, they're studied, and some of them, the first one I implemented, the third one, and the second one I discussed why it can't be used in the multi-steep model I shown because there are too many velocities. And other boundary conditions that we have, I will just go over these, the equilibrium on outflow. We are just forgetting the ones distribution functions that are going out of the fluid and normalizing the pressure, which in Lattice Boltzmann method, the pressure is taken in the simplest case linear dependent on the macroscopic density. So it just is multiplied by the reference temperature. And the periodic condition, maybe this simply implemented by just connecting 2 of the sets. Basically, if it's in 1 dimension of the lattice, you are just modulating the indexes while streaming. So how can we implement the full-way bounce back? The boundary condition that the velocity on the wall is 0. Basically, the simplest one for the T229 case. During the streaming, we have some recomputed distribution functions, and add which should go out of the lattice, and we add a set of nodes, ghost nodes into the wall, and these nodes basically, when they receive some distribution function, they flip it so that they can then model that the velocity is 0. So in this case, if f3 is larger than f5, and so the other ones which now we don't concern us, if it's larger, then everything is split, and in the next iteration it is moved into the fluid, so it decreases the velocity in that direction, so in the direction to the right, and then flips to the left, and this is like used to model this. It can be with second order approximation. But the problem here, when we have the multi-speed models, is that we can have some boundaries which are not just this wall at the edge, but we can discretize the objects in the fluid, convex boundaries. We can have some of the distribution functions going through the object. Basically here the green one is still okay. It should go here, but the red ones are going through some ball nodes, and because there are more velocities, there are not only 9 velocities, then it here goes through, and here it goes through the discretization. But yeah, here the question is if it should be considered, because after discretizing, there are also some methods which solve some boundary, the Lattice Boltzmann method with analytical description without discretization, but this is like the simplest one. It's more computationally expensive. So I also solved how to prevent these, but there should be not that many of them. Basically, here you can see the setup of the simulation with the inflow and outflow. The blue ones are the inflow. Here is the outflow. The dark blue ones on the top and on the bottom, and in the NACA profile are the ball nodes where the distribution functions are flipped, and then these dark ones are the fluid nodes, and these yellow to green ones are the sites where this can happen. So the sites for the D2Q49 model, 3 from some boundary. And on these sides, each time I stream the velocities, I have some additional structure. It's called, I call it third array. And I basically, firstly, I flip the dimension, flip the directions to get into this triangle, this sector. And then I go, if it's a large microscopic velocity like 3, I check if there is a wall on 2 or 1, and then here it's like it's the fluid node, so I don't need to check it. And the same thing for the non-diagonal ones for 3, I go to 2, 1, 2, 1, 1, and 1, 0. And if there is a wall, I load it into the data structure, because as can be seen here, there is not enough data space in the obstacle for even these ones. These can be saved somewhere in the obstacle. So there is the additional third array. And one additional method for this is to add some system of equations that the distribution functions should satisfy. Basically, you are trying to trying to get, there is the lattice side and there is some wall here denoted by the black squares, and you are trying to get to know the velocities that are coming in from the wall. So basically, you have the velocity that goes into the wall, like 3, 0 or 3, 1, but you don't know the velocity -1, because that should have come from here. So what you do instead, you set up this set of equations. Here, you say that the ansatz is that non-equilibrium parts, different non-equilibrium parts of the I and the flipped I, so the -1, for example, and +1 are the same. And sometimes they are also adding some momentum exchange. And for this, the equations can get complicated. Basically, for study of this, I try to map all the different possibilities for convex walls, because as can be seen, we don't know one of them, and one of them is known. But if it's a concave wall, we don't know both of them, even the eye, even the flipped eye. So this can be done only for convex walls. And after unifying the ones which are just flipped or rotated, we still get about 100 possibilities for the T2Q49 model. So the code sometimes said that this system does not have solution. And if it when it gave me the solutions without the solutions which it found, it still was a code which was few megabytes, so it wouldn't be sufficient or sufficiently fast to run on a graphics card. So for this, I just tried to add it to the Poisson flow conversion study. Basically, now there's periodic condition on the blue sides nodes, and there are 6 colors because there are 6 possible balls from this set. Basically, what I'm looking at is this. It's very small, but there are the ones where there are 1 row of walls, 2 rows, or 3 rows of walls. So here at the top and here at the bottom. And so this was the boundary condition for the wall. And just to give an overview of the inflow, we give for the Poisson flow when we are in the channel, we take the analytical solution for the incompressible flow and prescribe it for the velocity. And then when we multiply another step equation by the normal vector, here is just in the x direction, so 1, 0, 0. We get that the change of pressure is mu dynamic viscosity times the Laplacian of the inflow velocity, which is prescribed. And from this, we can get again, assuming that pressure is linear dependent on the density, we just get that the density can be calculated from the node into the lattice by adding the raw difference here, multiplied by the reference temperature again. And here, this is just the derivative, second derivative of the term above. And yeah, the outflow condition was already mentioned. Basically, I'm just normalizing the distribution functions such that when we calculate the momentum, statistical moment, zero statistical moment of the new function, it's 1, because this has moment rho, this is minus rho, and this is 1. So they just, by linearity, they add up. And the initial condition in Lattice Boltzmann method is usually, we don't need to solve the Poisson equation. We can just prescribe zero initial conditions for velocity. The initial condition for rho should be 1, just the reference value in the non-dimensional space, and then the reference temperature in my isothermal case. And then the simulation converges to the actual solution. So the numerical simulations, I was trying to keep them all in the same setup. So here the dimensions are 2.3 meters and 0.41. That's because I was comparing the results in the with the cylinder in the article by Sheffer-Turek, and these are the exact specifications for the domain. And then the velocity, the viscosity is very. Okay. The viscosity is 10 to the power minus 3, and the velocity is 0.3 meters, the maximum at the inflow, and it's increasing. So firstly, numerical study of my boundary condition on the wall. I basically took the one with the third array, where I flip everything, nothing is leaking through, and took it or applied it on a case, the edge case, where there is a hollow square. So one thick wall of wall nodes in the discretization, at each resolution, it's not given, it's analytically given just as the curvature curve, which can be the curve continuous or differentiable by parts. And then I try to run it with the leaking without controlling if the distribution functions are going through the wall. So the results with naive and fully bounded with third array look almost the same, or here we can see that they are actually the same, but when we look closer, I took a metric inside the square, which corresponds to the energy, kinetic energy, and yeah, basically I integrated the specific kinetic energy inside the square over the whole inside sector, and I got that with the naive scaling, with the naive fully bounce back, I have 10 to the power minus 8 the energy when computing in double format, and when I use the third array, it's basically 0, 10 to the power minus 32, or it changes to the diffusive scaling. This can be also seen that the diffusive scaling with the third array has some changes because the non-dimensionalized LBM velocity does not stay constant. Here the viscosity LBM stays constant, and here when it's acoustic, the LBM velocity is constant. The result is actually also constant for each resolution of the simulation. And furthermore, if we look at this velocity profile, we can firstly here, it doesn't seem like that much a difference. Here we can see the square. This is inside the square. But if we take the logarithm of this function, we can see that in the naive case, there is 10 to the power of minus 1 velocity at the side of the square, and inside there is 10 to the power of minus 3. So there is like 1% of the fluid is leaking, but 1% of fluid leaking to the inside, and then also 1% of this leaking to the outside is 10 to the power of minus 4 leaking air. So that's why we can't see any difference, but it can be seen for when we are doing some additional simulations that the third array might be in some cases more stable, because when I was increasing LBM velocity, this is taken also with the 0.3 meters per second inflow maximum, and then the LBM velocity, the non-dimensionalized, here is also something called the concept of speed of sound in the lattice, which is actually like for the D239, that's what we care about now. It's 1.01/3, and for the multi-speed model, it's larger. That's also one of the reasons why this model it does not have anything to do with the Mach number. It's just some variable used in the Lattice Boltzmann method, and this is because it's larger. That's also one of the reasons why the multi-speed models might be better to simulate the compressible flow, because usually LBM, the classical one, simulates weakly compressible flow. And here in the graph, we can see that when the velocity, here we have the speed of sounds, usually it's said that the LBM method works well for velocities not smaller than the speed of sound, and preferably like 3 times smaller to 0.1, so up to here. But if we try to for the model D249, the multi-speed, try to increase it even further in the naive method, the simulation starts collapsing or we get numerical errors. That's also one of the specifications of Lattice Boltzmann method, that the simulation is not always stable, and it stops at the 0.5 velocity, but with the third array, also the unit in energy integral decreases, but it works even for velocity 1 in the non-dimensionalized case. So here the third array actually works better, even when I try to not push the inflow velocity right to the maximum, to the 0.3, but when I try to increase it slowly, it's still the simulation crash. So for the this was the first problem. The second problem, convergence study for the pass-through flow, basically an overview of how close we are to the parabolic profile in the incompressible case. Here we can see the D2Q9 model and 2, but here it slightly changes with the entropic Lattice Boltzmann method. That's just that I am using for the equilibrium, the entropic extremum, and not the second order Hermite polynomial. That's closer to the 2. Actually, the result is just so that always rounds up to 2. But then the non-equilibrium bounce back, which I use with the 6 boundary conditions, it actually works like with order of convergence 1, and then it stops working completely. Here we can see the error normalized is 1, so it actually just nullified all the flow in the channel and stopped working for the large dimensions. And the D2Q49 model is more chaotic than this one, or this one. But even for a smaller resolution, here is 5,000 times 1,000, it gives the same L1 error. But what is important to note here, the D2Q49 having 5 times more populations is much slower, and these simulations took a few days. And these ones took at most 1 day. So for the last part, the last 2 simulations with the obstacles, firstly, to discuss the drift and lift coefficients, basically, we are just integrating the stress tensor and taking the element here, the first one, because the x direction is in the direction of the flow, and then the second one for the lift. The U overline is just the average velocity. Here in according to the Sheffield, we are taking the 2/3 of the inflow velocity, and the dimensions are just the dimensions of the object. And also one of the specifications that we are in 2D is that the third dimension is set to unit value, so set to here 1. So the P3 is actually in the 2D simulations on the 1, and we end up with the 2D case. So just from the discretization of the object, which is just pixelized, we end up in 2D with these 4 normal vectors, and that are in the integral of the stress tensor. So actually here in 3D, we get 6 of them, but I have used only in the 2D, but now I'm implementing it all in 3D and doing the same simulations in 3D with some additional ones. So here we have the 3 sets. Basically, we take the middle of each boundary, split it into groups by the normal vector. So green group of the nodes, the side which will approximate the integral is the normal -1 and 0. And for these, we look at the closest lattice side where we know the macroscopic variables where the fluid is. And from these sides, we have the close values, the closest macroscopic velocity we know. And basically for the normal vector 1, 0, 0, we know that the two derivatives by the second component and third component of x are 0. Basically here, for the second component, this derivative in this direction, the vertical one, is 0 because the velocity is constantly 0. And the derivative in the normal direction will be set to just a linear interpolation from a linear interpolation from the closest velocity. We just get this derivative 2 over the step in the lattice, now in physical units, and the physical macroscopic velocities. And for this, basically, we can see that if we add all this up, the divergence is not 0. It's a non-zero value. So here it presumes compressibility. And we can write the direct force from the groups, approximating the integral and splitting it into the groups. And two groups, the S1 and S2, which have the vectors 0, 1, 0, 0, and minus 1, 0, 0. Those ones in the direction of the flow are added with the pressure times the identity, and the other ones are just with the dynamic and stress tensor. And if we input all the known variables in the dynamic stress tensor into this equation, we get two possibilities. One is when we presume that the trace of the D matrix I showed at the beginning is 0. That would be the second one. There is no minus 2/3 from the Stokes hypothesis. So there is just 2 over dx and the two coefficient before it. And if we presume that it's still compressible, this incompressible case was assumed in the Schaffer-Turek article I was trying to reconstruct, and I also computed the ones when I assume it's compressible, as I'm assuming also that it's compressible when computing it, and then I'm increasing the velocity. So it should be more consistent and all compressible, even though it's just weakly. So this is the setup of the simulation, basically the same as with the knuckling. I'm using the third array, and also there's the setup in IIO method from simulations I computed for reference in ANSYS, and from the Lattice Boltzmann method, we can get these results for different inflow velocities. Here I included even the larger ones, which did not finish or crash before finishing. But I was trying now for the diploma thesis to recompute some of these simulations, recompute some of the results with the actual result, even for the larger velocities, with some success now. But what can we see? There's 3 ones for the Schaffer-Turek. We have the stable one, 0.3, where the drag coefficient is around 5.7, and then we have we can see that there are some harmonic oscillations happening. Actually, in the flow, we will see that there is some vortex flow for the larger velocities. But here, also the lift coefficient, that's much more chaotic because the simulation is almost symmetric. It just shifted a little bit. The cylinder is shifted a little bit to the top. And the result here, they're stable only in the 0.3 meters per second. And maybe I would like to also comment that they are slowly increasing, not because the velocity is increasing, because the inflow velocity is given, but not because we are approaching from the equilibrium set at 0, but because the inflow velocity is also interpolated so that the simulations are more stable. So during the first 25 seconds, I was increasing the inflow velocity, the maximum inflow velocity from 0 or the hundredth of this value to this value. So here also we can see how it increases. Then it's also has some weird spike. Those can be seen also in these simulations for the larger velocities, and the other ones, like from them, usually maximum value is taken. So here, firstly, a table of the results with maximum lift coefficient. So 3 LPM methods as before, then the finite value method, and then the reference from Schaeffer-Tech articles. Basically, here there are also 2 methods to compute. Schaeffer-Tech ST assumes that it's incompressible when computing the dynamic stress tensor, and without ST, it assumes that it's also compressible when computing the stress tensor. We are trying to achieve the value 0.01. Here, the reference method does not work that well, but for the drag, it actually was closer. In some cases, as I will show, but we can see that there are some differences in the model. Maybe the multi-speed model is the closest of them all, 0.55, 3.2, when where other ones are 0.7, 0.6 for the first case. And for the drag coefficients, which are not taken just as an approximate or the mean value after the flow stabilizes, so from 25 seconds to 50 seconds, so that the harmonic oscillations are average. We can see that the reference value is 5.57. The finite value method gives us 5.57 and 5 to the end, and here the multi-speed model is close, 5.77, and the single speed models are slightly larger, around 6. Here these are the missing results because the reference values were just for 2 speeds, and here these are the simulations which didn't complete, just the smallest 15 meters per second, but I'm trying to recompute them and change the time step so that they don't crash. And here you can see the velocity profiles of the Lattice Boltzmann method and finite value method. And here the pressure profiles. Yeah, here this is just, these are the 2 methods, and these are the outline and velocity profiles and pressure profile. So we can see the pressure here. The difference is its density, but linear, just a linear scale pressure in Lattice Boltzmann method. So the difference is just 2% in this case. We can see that higher pressure, higher microscopic density is at the object, in front of the object, and then we can see that throughout the whole domain, the pressure, the density linearly decreases, both from the inflow condition that the pressure gradient should be equal to some value. And here for a larger inflow velocity, for the velocity 3, we can see vortex flow in the case of Lattice Boltzmann method, and in the case of ANSYS with finite value method, I used K omega model, so it was actually most probably just modeling the averages. So it's slightly average throughout the whole domain. It can be seen that it's not that of a fault. It's not can be seen that it's a vortex flow, or it's not a vortex flow in this case. The modeling here, just as a note, now the new simulations with high velocities at the inflow give very chaotic results. You can see that there is like the boundary layer is maybe just splitting from the boundary, and there are some very high velocities that here the scale actually be times 10, just didn't change properly. And for the pressure, here the difference is about 15% in the density, so in the pressure. And we can also, maybe from this, you can see the equipressure fields behind the obstacle. But this is mainly, I think, influenced by the fact that we are taking it with the walls in the channel. If we took some far field flow, that there was a symmetry condition or just free condition that they can leave, and the inflow is in the might be more stable simulation, and it could be closer to the compressible flow. And the same simulation was done for another object for the NACA profile, also with the finite volume method. The results at the maximum velocity, the 30 meters per second, the Reynolds number here is smaller, so it could the simulations work even for the larger velocities. Here also vortex flow, just small vortexes. Here it's everything is average. For smaller velocity, they are almost the same. And for this, the direct coefficients are actually decreasing, as we can see. First, they start here, decrease, and the harmonic oscillations are very slow, very subtle. And the lift actually is more stable here, as the Reynolds number is smaller. So here, again, it's increased. Here we can see some of the waves which are in the fluid. So the lift coefficient is affected by the waves, but then stabilizes. And the whole table with the values now without the reference, because the NACA profile was not in the particle, you can see that the direct coefficient decreases, and the lift with finite volume method actually increases, as for NACA link it should. But the Lattice Boltzmann method proved not to be good for the lift, as it's very small and actually decreases and goes even to the negative numbers. So I think that it was like sufficient or good enough for a graph, but not good enough for a lift. Here the final chart, just you have the two objects, the blue one, the blue and green lines are the two methods used to model the shepherd direct flow, the flow around the cylinder. For the low Reynolds numbers, low inflow velocity, they start with direct coefficient around 6, and then it slowly decreases and then stabilizes at some value. Here, it might be useful to have more computation, so that's something to do in the future. But for the wing, it decreases very steeply. So for low velocities, the wing actually has higher drag than the cylinder, but for high velocities, the wing has much smaller drag than the cylinder. You can maybe also see that Lattice Boltzmann method and simple, the difference between them has some error which is consistent along the values. For example, the blue line is always above the green line. Lattice Boltzmann method always gives bigger values for the drag. Or in the case of cylinder, but smaller in the case of a wing, the NACA profile. And for the so this was for the simulations of drag profile. And lastly, just what I'm working on now, I'm extending it to the 3D. So here's some of the first simulations in 3D. And in the future, I would like to now try to create a reduced multi-speed model so it's faster. Because in 3D, the model D2Q49 should be D3Q343, which is gigabytes of memory even for small lattices. And I have already incorporated it into template numerical library, which is a library that is developed by the mathematical modeling group at our faculty. And basically, this is a template numerical library and the module Lattice Boltzmann method, which is can be found on GitLab, and there are some test simulations which you can run yourself. And I would like to apply this multi-speed model on a 3D bounding channel problem, which is studied by NASA, and maybe in the future try to find out when the entropic lattice Boltzmann method is really needed, because it actually with the entropic lattice Boltzmann method you can then satisfy the condition that the entropy increases always. Yeah, here is also a summary of the work, and this is the reduced D2Q27 model for in 2D. And for this one, basically when you have a model, you need to find out what are the weights of each discrete velocity, and then you can try to find the equilibrium by entropy of this Boltzmann method or the second order semi-polynomial. So I think it was very exhausting, but thank you for your attention. And thank you for having me here.